Want to hit record? All right. Good morning, everyone. Thank you so much for joining us today on a pretty frigid Tuesday morning. This is our final webinar of the year for TURI. Our webinar today will focus on how people are using AI to support toxic use reduction, safer chemistry, and we're really excited. We're joined today by four experts. We have our own green chemist, Dr. Gabrielle Salerno. We have AJ Kenny from Smarter Sorting. We have Alicia McCarthy, also from TURI, who will be presenting on one of our student projects. And we have Dr. Jakob Kostal from GW University, who will be presenting his research. Um, I'm not going to take too much time at the top, but I did want to highlight while everyone is here a save the date. This spring, the Spring TURI conference is back. We will be hosting it on April 8th 2026 at Coburn Hall at UMass Lowell. We really encourage you all to mark this on your calendar now. Registration, agenda, speakers will be forthcoming, but please save the date, April 8th. We'll be really excited to see everyone in person again. It'll be a wonderful venue and a really great way to showcase all the work done by you at companies as well as our academic partners. Um, all right. So I am going to stop my screen sharing and I will let Gabrielle start his slides. Let's see. Gabrielle. All right, so Dr. Gabriel Salerno is TURI's green chemist. He has a background in industrial chemistry, and he helps lead our research program, working with both companies and academics to develop safer alternatives to toxic chemicals. Gabriel is also a professor at UML. He actually just came from teaching his class, and he works hard to teach the next generation about green chemistry. All right, Gabriel, take it away.
Hi everyone, thank you Agnes for the kind introduction. I want to touch base before our guests, that know much better than me about AI, start speaking. I want just to touch base on a few basic concepts. Like basically, I want to say at first of all, that AI isn't magic. It's just as any other uh, huge engineering feat. It has a lot of well, in this case, statistical and information theory foundation, and then we build up upon that to create powerful prediction models. Of course, and there are some trade-offs that we have to be aware of. For example, interpretability, when that is very important for when you are in the natural sciences. And then we have the AI is a super big set of tools, but basically you can say that are systems that replicate intelligent behaviors through learning from data and applying predefined rules and algorithms. And then you have the typical large language models, which are basically the hype of the moment, but there are other tools that are earlier than that and super useful that we are going to touch base too. And then generative AI will learn from that data to create new content. Could be text, computer programs, and then the ultimate goal, the holy grail of this is create machines that exhibit superhuman-like intelligence. And then, I want to touch base on the super basics because I mentioned the foundations on statistics. As any model has parameters, and those parameters have to be fit to data. And for example, for a linear regression, we have a concise formula that is super interpretable, and we like it a lot. But it's not fit for any problem. For more complicated problems, we had to find the model and those parameters in a different way. We don't have a formula. But there are things that are still true, that, for example, data quality outweighs quantity, and that's true for linear regression and for 10 trillion generative AI models. And the more complex the model, the less meaningful from a epistemological point of view, if you want, from a natural science point of view, it's harder to interpret the parameters, and there is a more risk of overfitting, like a kind of get too comfy with the data, and potentially have problems in prediction in uncharted maps. So, and then we have these two important concepts too. One is verification. We fit, we have a set of data, we train the model, and we get some parameters. And then we get a model, a characterized model, with all the parameters. And then of course, good models. We don't train models, to just to strike a pose. We want them to we want to test them to see if they can if it has predictive capabilities. So the training it's about verifying the model if the model is good for the data, and the validation is about prediction. And also for linear fitting or super AI, correlation is never causality. Sometimes it matches, but it's not necessarily true. And not everything that fits then can predict. Sometimes something that fits very well in the training fails at testing. And here we have one like this typical basic Datasaurus docent, that all of these data sets have the same mean and variance. So, but if you see them, they look very, very different. And that's what happened. Now imagine trillions of parameters or trillions of, of dimensions. And I said, models are as good as their data. We have this saying called garbage in, garbage out. Of course, machine learning is a little bit more, we can kind of overcome some noise, and maybe classical statistics is very, very sensitive. But still, we need to take care of the quality of the data. We have to do a lot of work in data curation, and try to validate our models against different sets of data. Otherwise, we could incur into echo chamber where we have an overtrained data, overtrained model to some exclusive type of data, or hallucinations, misleading outputs. For example, here we have the gymnast. Like we are training, we are trying to, we are asking the impossible to the computer. We are saying, okay, give me a gymnast, which is a super complicated physics, and we are giving the computer just pixels that change. From a point of view of a computer, we are just giving them some pixels in a flat in a flat surface, and the gymnast lives in 4 dimensions, so it's or more. So that's one example of hallucination for misleading the model. And then, now coming back to our everyday job, we do a lot of alternatives assessment to try to make our workplace safer. And when we have our alternatives at hand, we ask 3 main questions: Is it safer? Is it effective? Is it affordable? And from there, we try to use the tools that we have at hand to answer those questions the best we can. For example, we have our P2S system that many of you know. We compare EHS hazard categories using quantitative and qualitative input, and each category is rated using values, key phrases, GHS classification, and we depend upon available data. Now, data, especially for novel entities, either if they are good or bad for the environment and for public health, we have many families, entire families of compounds that we don't have even in the biggest databases. We don't have data available, so we had to resort more and more in computational toxicology. and AI in that sense, it's very promising. For example, well, first of all, we can go beyond the SDS, trying to be beyond the websites that we are used to our go-to websites, and say, okay, let's see in the literature if there is any information about my compound of interest. Uh, one thing could be reading the entire internet, or reading a big amount of PDF to automatically gathering hazard information. There are some challenges that well, Alicia is going to take a, a deep dive on that, but we know that it is important to supervise, to avoid a risk of hallucination, of making up a hazard that doesn't exist, or overlook a hazard that is very important, and it's a really a thing. So, well, this one, there are many tools that we can use, and they are considered AI, machine learning, deep learning, beyond the normal statistics that for quite a long time it was dominated by least squares and principal component analysis. Now we can go beyond that and use stuff like variational autoencoder, support vector machines, that I imagine that Jacob is going to enlighten us a little bit more. But these tools can take quantitative data and qualitative data together, and the architecture, like accept numbers and categories all together, and they can identify cluster constellations of molecules that are organized by their motif, by the functional groups. And this is very important when we want to predict properties like toxicology, or physical properties like flammability, or a density, or a viscosity. And that helps build something that we call QSAR decision trees. QSAR decision trees that now is very common, is a QSAR toolbox that is not AI, but it can be empowered by AI. And basically, it's a decision tree that you divide the universe of molecules into classes, and when they have several motifs and several descriptors, we call them, in common, we can call it kind of a cluster, and from that cluster we can do a regression, and sometimes that regression is based into something that we can explain, and we can defend when we say, okay, the, the, the little dose 50 or X amount, or X compound has certain order of magnitude, and that could be or could not be of concern. Another hazard of concern that is very important in the industrial settings is flashpoint, ignition energy, stuff like that. And for that, we really need physics-informed descriptors that are much more data efficient, and you might need, instead of having a data center trying to figure out the entire universe of molecules and descriptors, you can really even come back to normal statistics to work with. But the automation of this, or deciding if using one complicated model or something a little more simple, can be automated using AI. Actually, at TURI, we use a rather old software, but pretty, that has some AI features, or like say classical AI features, like genetic algorithms to calculate solubility parameters, solubility predictions, interaction with polymers. And now we have a new tool ASCOS MIT is a project from MIT that can like give you some synthesis optimization based on the descriptors of the reagents and the products, can calculate solubility quantitatively, and the approach is a little bit different. This is more quantum in the case of ASCOS. HSPIP is a little bit more UNIFAC thermodynamic. So we are using AI to predict solubility already. And pushing this forward, we have a research grant now um, that we are working with Worcester Polytechnic Institute from September, and the objective is developing a machine learning tool to identify low toxicity, low cost solvents, replacing a Tura chemical specifically for dissolving PVDF, a polymer, a fluorinated polymer in battery recycling. And the first thing is check the universe of solvents, to find the Hansen solubility parameters. And then from there, try to find also single solvents and solvent blends up to 3 components. And we scrape the internet to find GHS hazards, and also bulk pricing comparison. And from there, we do, our partners in WPI, Michael Timko and Muntasir Shahabuddin from WPI, they are optimizing this using machine learning tools to make this to grab these important descriptors in the field of solubility and in the field of hazard evaluations. And of course, if we tackle this problem, this tool is developed for this, but the tool is completely generalizable. The framework can be applied to accelerate any safer, affordable solvent identification and selection. So we have the three things: performance, the cost, and safety in one go. And then on the other hand, we have some pitfalls. We had to be very careful about overusing or abusing of AI. Over relying. Over reliance on AI. We are seeing some cognitive debt in students. There is an MIT report that found that from a brain activity point of view, overusing AI could harm cognition. At the same time, although the hype is that AI is going to replace humans and stuff like that, it seems that it is too early for that. 95 of generative AI investment are yielding zero or even negative return of investment, and that's because there are a lot of overhyping, and it's hitting really hard, and the CEOs that decided too fast on finding too many people are getting kind of they are rehiring many of these big companies that started, they are rehiring because, for example, lack of empathy or error prone things that are not foreseeable during training, because during training everything is, kind of like in a lab, right? You can train your on the data, but then when you leave your tool in the wild, you have to be thoughtful, and human oversight is going to be essential for a reliable development for using AI. So, and then on the other hand, there are some risks at a society level, and the EU and the US, they know that. In the EU, they have this EU AI Act that is a centralized regulation, and they classify the AI applications in an acceptable risk, high risk, limited risk, and minimal risk. Minimal risk are games, some type of chat box, spam filter, translation. Limited risk will be something like generative AI, um, LLMs and stuff like that, and they have some requirements. High risk could be toys, cars, medical devices, all of these kind of toys that now have AI and interact with your child. I will be very careful on what could happen with those. And then unacceptable risk, for example, social scoring, real-time remote biometric identification. Those pose a clear threat to fundamental rights, so those are unacceptable. And then there are differences between the regulations in the EU and the US. The US is more sector specific, the EU is risk based. They have, EU has clear risk levels. In the US, we don't have a formal risk classification, and then the enforcement is more centralized in the EU, and here is more given the freedom for each state and stuff like that. And then on the other hand, we spoke a lot about the software, but what about the hardware, right? So it is AI is very, very hungry in data, in water, and energy. Uh, so it's very, very, we really, really need to consider the electricity consumption that could and we are seeing a lot of pushback from many communities where they have a data center that uses a lot of energy, and the electricity bill goes up for everyone in the community. Water cooling, we had to cool the data center hardware because it's a lot of data flowing and electricity flowing, and the water cooling could be the use of water for cooling could be as big as an entire country. And then talking about toxic chemicals, there are some technologies that over rely in PFAS, and I would say, if you really, really don't need that level of cooling, I would suggest not to use boiling PFAS in your server room. Of course, for some applications, I don't know, maybe computer vision for self-driving cars, or I don't know, military applications or whatever like that you really, really need. Well, okay, maybe I cannot tell you, don't use these technologies, but uh, most non-PFAS volatiles are either flammable or material incompatible. So for two-phase immersion cooling, which is kind of the biggest heat rejection because they have liquid fluid flow, but also heat removal from vaporization. That's the biggest heat rejection. So for very highly competitive data centers, maybe they will use this type of technology for for uh, yeah for cooling, for primary cooling, because you have primary cooling, directly your hardware, and then you cool the coolant with water. So the water usage is always for secondary cooling, and the primary cooling we could use different things. Of course, air is not enough. That's why we have to do either liquid immersion cooling, direct to chip cooling, or two-phase cooling. So far, two-phase cooling is highly dependent on PFAS, highly reliant on PFAS, is high complexity, higher potential for leaks and cavitation due bubbling. So it's not a panacea either. We have some technical problems that are being reported or for two-phase cooling. They cannot not justify, kind of guarantee 100% containment of the PFAS, especially boiling PFAS. So I would say it's a risk that should be only for extremely essential applications. but liquid immersion cooling and direct to chip cooling, there are PFAS free options available. Actually, liquid immersion cooling is absolutely PFAS free. So to give time to the rest of the speaker, I would like to say that AI can help TUR by bridging data gaps, like using user predictions or document parsing, and it could help streamlining alternative assessment if you want to do a pipeline, and you want to code it, hard code it, AI can help you on that. Or there are already companies like Smarter Sorting that could help you streamlining those alternative assessments. However, interpretable models are essential to ensure reliability. Still, intelligence assessment is a applied natural science. So the more interpretable your models, the more trust you can have on them. And then the reliance on data centers that consume amount of energy and water is also something that you should consider in your operations. Do you really need X amount of AI, or you can use less, because that means energy and water consumption. And some data centers might rely on PFAS for primary cooling, and then over reliance can lead to cognitive sedentarism. So with that, I would like to thank you, and I would like to I am open for questions now or later.
Thank you so much, Gabrielle,
No, thank you. Thank you.
for bringing up just a wonderful background in machine learning and AI, and also presenting some of these really difficult challenges, particularly between using this new technology and also using our other resources. Just for time, I would encourage people to ask questions in the chat, and Gabrielle, maybe you could monitor the chat and answer people's questions there. We're going to shift over to AJ Kenny, who is going to present on smarter sorting, which is one of the companies Gabrielle was talking about. AJ, you can go ahead and start sharing. So AJ joins us from Smarter Sorting to talk about their AI agents, which help companies manage regulatory, compliance, and chemical hazard information. AJ has a background in environmental science and soil chemistry and has been spending the past 13 years working across the regulatory landscape. And as AJ said in his bio, he has a genuine love for reading rulemaking. So you all are in good hands here for someone who can help make the regulatory world a little bit simpler. All right, AJ, take it away.
Fantastic. Hopefully everyone can see my screen. Um, yeah, maybe just a quick background on smarter sorting. So we work with some of the largest brands and retailers in the country. We provide regulatory classifications and other product data to help them make better decisions with regard to storage, waste, transportation, EPR programs, chemical restrictions, you name it. We try to think of ourselves as a one-stop shop for um, regulatory navigation and solutions. Um, and as Gabrielle said, you know, AI is, it should be a tool, not necessarily something that is, or at least in my views, like not something that we want to just like say AI is going to solve this problem and give it and let it run. So we consider ourselves to be heavy users of AI. And I stress that because humans are ultimately accountable, and that is kind of like my role within Smarter Sorting is that, if we're going to deliver a high quality data product to our customers, someone has to have some human oversight, making sure that the model is putting out high quality data. And if it's not, we'll kind of introduce changes to our agents or even insert some classic Python or SQL into our overall data flow. So with that preamble, I just want to let you know I'm going to demo some practical tools that we've built that use AI, and hopefully it might spark some interest or ideas in your heads. So one of them that you should see on the screen is it's called an RSL ingredient screener. RSL is restricted substance list, and that can have many different interpretations for many people. Sometimes it's seen as a retailer has a list that they've published, and they said that they encourage their brands that they sell to not have these particular ingredients in their products. Um, but really, at the end of the day, it's a list, and it's a list, and it could be this is a hard chemical restriction, or this is a soft. We prefer that you do not put these products in, or maybe you're not going to get a badge from us on our website until you can guarantee that these chemicals are not in your particular products. Um, So what I wanted to do was, let's see what I got here. I made a list of about 5 products, just a name with some ingredients, and I'm going to put one in here and kind of let you just see what it looks like. So I'm putting in my barkeeper's friend and the ingredients I've got here. And again, this is publicly available ingredients list here. So I'm just putting these in here, and I'm going to select from my list of RSLs or what I want to screen against. So where's my tour? There's Turi. There we go. So I want to screen against the tour list. And maybe we want to screen against Credo, which is kind of like a more of a beauty type chemical restriction. I'm going to hit screen. And so the first thing it's going to do is it's going to take the ingredients that I gave it and it's going to parse it into distinct chemical identities. So I'll be honest, when I first looked at this ingredients list, I couldn't tell you that there was just 2 ingredients because we've got like some comma separations here. But this is, one of the cool things about AI is it's going to identify this is a single chemical ingredient, this is a single chemical ingredient. I've now determined that these are some single chemical ingredients. Now I'm going to take the ingredients that are listed in this Credo list and the Turi RSL, and I'm going to compare it to every single chemical or chemical group that's listed on these in these 2 lists. And of course, on the right side, we have like a nice little readout for someone. Say you wanted to compare against like dozens and dozens of lists. You may not know exactly what these lists are. So we've got a nice little primer as to what is the Credo dirty list or what is the Turi RSL. So someone can come in here without a whole lot of knowledge and they'll have some background. And one thing that's super cool is adding an RSL in the advent of AI is amazing because when I started out, it was really just very prescriptive. If you want to screen against a list, you have to have a CAS number. You have to have a chemical name that matches identically. It has to be structured in a very, like in a CSV or a JSON file. Like it had to be very particular. But now I can tell you that these lists, they could be CSVs, Excel files, PDFs, scanned PDFs, Word documents. And that's one of the amazing things about AI is it can just take any form of document and perform these types of screens. And one of the complexities here is, a lot of these, everyone may not be familiar with each one of these lists, but a lot of chemical restrictions are going to be at the chemical group level. So it may say no parabens. Well, one of the cool things is AI is going to say oxalic acid, is this a paraben? So it's actually going to perform like a chemical group level assessment against the list. And so it's a pretty heavy analysis, which is why you saw it took a few minutes to actually get off the ground here and actually shoot. So we got one going here, but I wanted to show you, you can actually, with our tooling, you can drop in into like what we call batch mode. So here I've dropped in 5 products and I'm gonna hit like a green seal list and Prop 65 and I'll let that run. And the reason I wanted to show you this one by one versus this batch mode is that one of the other cool things about AI is that unlike me, it's very good at multitasking. I can run it in parallel processes. I'm barely good at doing one thing really well. So the fact that it can do the same thing extremely well, in parallel is a definitely a time saver. So yeah, we got our list. We tell them what it is. We screened. We look at this full product analysis here, and so there's a few different tabs we could toggle between like a product summary, the ingredients list, and the RSL details. So one of the interesting things, if you have ever had to do restricted substance screening, is you may say, well, this is I'm doing barkeeper's friend, which is typically like something you might put in your sink or porcelain or clean some glassware. Credo is a beauty product and chemical ingredient screening. So first you may want to know, is my product even in scope for the screening process? Because there's tons and tons of products which may say, is this a leave-on conditioner or a rinse-off product? Is it used in cosmetics? Is it used for surface cleaning? And so when you perform a restricted substance screen, you kind of want to know, am I even in scope for this assessment? Um, Oh, there we go. Okay, so I flipped over back to the batch side to let you know, just to give you a view of like how this is running parallel products. I ran five here in the same time that basically it took to run one of these products. And so at least for the green screen and Prop 65 lists, nothing is getting flagged, which is okay. Now we are going to get some like additional AI insights, which is going to say what are the ingredients of concern for each particular product. So I threw Febreze in here and it's saying, okay, well, fragrances is a generic term. And I think anyone who's looked at the back of a label knows that, or maybe you don't know, but like you don't actually have to declare what's inside of a fragrance. There is some rules coming out about fragrance allergens, and which you may have to post on there. But fragrances in general is it's flagging and saying like, hey, I don't actually really know what's in here. It's a generic term. Um, so that's very cool. And so really, I guess to kind of sum it up, if you wanted to say like, well, do any of the ingredients or chemicals that I'm using in my process would they be subject to TURA? And like, should I be thinking about an alternatives assessment? I mean, with these types of tools, there's not a whole lot of like reasons that you can say, hey, if I get an ingredients list, I can slam it up against the TURI list and I can get, without doing a whole lot of work myself, a kind of a clean list and say, here's all the ingredients and the products that we've screened, and here are the ones that you may want to consider for an alternatives assessment, or here are the ingredients that were flagged and why they were flagged. Um, okay, so that's one particular example of using AI. Another one, which I think is pretty fascinating and not really talked about a lot, is something called vector embeddings. And maybe you're thinking, what the heck is that? I still say that maybe once a week, and I refresh myself. But this is this is a map, and it's 1.3 million chemicals that have been embedded into an embedding space. Now, you can zoom in and you can see all these little dots. Each one of these is a particular chemical name. And if you might see on the left side that like the CAS number is changing or the chemical name is changing. And there's all sorts of different tags for these. So we might see here's phenolics or phenols. And then so what these are is it's basically like a fingerprint for the string here. So this ingredient name has a particular fingerprint under an embedding model. And I just want to give you a real taste of what that looks like. Um, so if I wanted to create an embedding for the word ethyl alcohol, I can hit, and happens to be an OpenAI embedding model, and it's going to give me this, I think it's like 1,500 different vectors to basically say this is the fingerprint of the word ethyl alcohol. And so what you can do with that is you can come into a tool like Nomic, which is one that we use, and say, which of these are, uh, hopefully I spell this right, phthalates. And what's really powerful about vector embeddings is it's 1.3 million products, and that's a lot of data. Vector embeddings basically supercharges your search because it's doing a data analysis on the fingerprint. And so when we say which of these are phthalates, that's an analysis that a human might take 50 hours. Or if you wanted to put this into a traditional large language model like ChatGPT, it's going to say like, that's too much information. But with the power of vectors, you can say, all right, I want just really tell me which are these phthalates, and you can kind of limit it to like what are the like highest likelihood ones that we've got here. So we get and this is what's cool about maps is you get a little view as to like how they are concentrated. So all of our phthalates are concentrated in this particular area of the embedding space. And there we go. There's the word phthalates. All right, here we go. So we got benzyl butyl phthalate, uh, phthalate, and depending on how you may want to screen ingredients, you can kind of give yourself a little bit more in scope if you want to cast a wider net, or you can go really, really hyper into like what is the most phthalate thing of all phthalates. And the reason I think that's cool, and I am trying to be time sensitive because time management is not my strong suit, is that we can take that chemical fingerprinting technique of embeddings and you can apply that to documents like safety data sheets. And so I'm going to take a Loctite document, send it through. This is our standard parser that we use. And so we get some metadata about the document, how much of it was parsable, 80%. This is a tier one document, which just means it passed all of our tests. And then you kind of get an SDS that's been translated into a more data-friendly structure, so you can actually do things with it. So what the next thing I wanted to show you was you take this fingerprinting concept for documents, and I embedded a bunch of these components of a document. So the GHS hazard statements, the CAS numbers, the flash points, the you know the proper shipping name and the DOT section. Um, and so then there's another angle of this tooling that is really powerful on the embedding side is I uploaded 16 documents, 16 SDSs, and I can show you what they are. We've got Pine Sol, fabric spray. I got my barkeeper's friend, a liquid Flitz metal polish, bleach. And so you can, because now that you've embedded them, you can actually ask questions the same as we were doing in this map. Like which of these are phthalates? You could say, which of these are skin sensitizers? Oh no. Let me try and refresh this. Oops. All right. Let's try which of these sensitizer. Okay, seems to be running now. So what it's going to be doing is, and again, you could do this for 10 safety data sheets. You could do it for 100, 1,000, or 1.3 million. And it makes search and like being able to ask questions of your documents and your data super, super fast. And so it's telling me of these 16 documents you uploaded, one of these is a skin sensitizer. It's the Flitz metal polish. Here's the key ingredient. We can even have a link to the SDS as we've uploaded it here. And this is something that is, I think is super cool because I got my start in GHS land when it was coming out in 2012. So I wrote a lot of safety data sheets. And so I have a soft spot for H phrases and employee safety. And you can even, in adding data is super simple as well. Um, One of the things I was going to add in here was this Loctite that we just looked at, this Loctite SDS. So it's just a link to the safety data sheet, and we're uploading it, we're parsing it, we've turned it into a vector, and now you can see we've got 17 documents indexed, and I'm going to say, tell me about the hazards of Loctite. And so now it's going to answer the question in a natural language, but it should be looking at those vector embeddings for the product that we just uploaded, which is the Loctite document. So it's saying like, well, um, skin irritation, allergic reaction, serious eye irritation, and suspicion of causing cancer. So it's got those H phrases laid out. So I think this is super fascinating because you can do this for any document, any set of text, really, and you could create your own little library of, hey, I've got 5,000 SDSs that I'm working with, and I want to know about the skin sensitization hazards, and maybe I want to consider replacing those for exposure to employees. So that's the end of my demo, but I really want to just kind of show like the two sides of it. There's large language models, which are really computationally intensive, especially if you want to use um, like different chemical synonyms. And is this part of a same chem group? That's got a lot more reasoning that's built into it. And so that's why you saw it took a little bit longer. But if you have a huge sets of data and you want to ask some more pointed questions just to get you into the right direction of which product should I even be looking at, you can do something called like vector embeddings, which is really going to supercharge how you may assess the chemicals that are used. So
Wow,
hopefully that, yeah, go ahead.
thank you so much. This is excellent. We have several questions in the chat. So first question is how frequently are the RSLs and the RSL screener tool updated? Like how does that stay? Does that stay live? Does that have to be inputted every time there's an update?
So it is up to like this is a I'll just be real, this is a demo UI. So
Mm-hmm.
our actual RSL screener is built by actual like software developers and engineers. I'm, yeah, as you know, like a regulatory nerd who can vibe code. Uh, so, but honestly, it's this is the great thing about it is like a person who wants to own this RSL tooling and for a customer is like they don't have to worry about like, is my formatting right? Um,
Mm-hmm.
you can just say like add RSL and you can go um, insert the URL to where that RSL is sitting. And so
Mm-hmm.
there's sorry, to answer your question, there's two sides of it. One, you could do it manually. Two,
Mm-hmm.
Charlie, who wasn't here today, is our CEO and co-founder. He actually has, and like we do have another version of this, which is constantly web crawling and saying like,
Okay.
is there a refreshed RSL list? If there is, let's bring that in and version it.
Okay. So there's both you could manually update, and then there's also a version that's sort of continuously checking when things are uploaded onto the internet. Great, thank
Yes.
you. And then there's a few different people have asked just how these tools can be accessed. Is this something that is available to the public? Is this a subscription? I know this is
Mhm.
a demo that you're showing us, but just curiosity on how to access these types of these tools from Smarter Sorting.
Yeah, I would say if I think you're going to share my email address, you could
Hmm.
maybe like message me with your specific use case that you have in mind, if whether it's RSL or creating a document library that you can query with safety data sheets or anything really that your mind is coming up with, and then we can
Hmm.
figure out like, do we already have a data product that fits what that person is asking for, or is it something that might not, we're definitely open to developing things together with folks who have very specific use cases.
Gotcha. And yes, we will definitely share your email with folks. So to answer several people in the chat, um, just reach out to Smarter Sorting to see on a case by case basis to access these different tools. Um, and another question, this is a kind of hefty question, so maybe just a an overview or summary of um, let's see, where did it go? Someone, or Topher Buck asked, just for an understanding of how Nomics decides which of those 1.3 million chemicals are phthalates.
That is a heavy question, and I will say I'm not a data scientist, but similar to what this question is doing, it's taking your your question. So my question here was, which of these chemicals are phthalates? And it's actually, we can do this. You can still see my screen, right?
Yes.
It's going to turn that question into a vector. So that it doesn't have to, you can get a little bit wild with it. You can say like the question is now its own vector. It's got its own coordinates, so to speak, and it's going to plop somewhere on this map, and the proximity in this 1500 dimensional space is going to say it's going to then ask the questions of everything that's within that space. So we call these like nearest neighbors. So that if your
Hmm.
fingerprint is close enough, it's going to ask questions of everything in that area where the embedding is really similar. And so it's going to say like, all right, well, you were in scope for the question, but you're not a phthalate, or you are. And it's got this when you see this populating here, I think this would be a way to control how broad of a net you want to cast with the similarities. So there is a lot of user control as far as, I could say, and I guess this is something that I won't be the best to speak to, but this idea of neighbor matching, like how do I know when a neighbor is close enough?
Hmm.
And we've got some actual data scientists on our staff who help us determine like these thresholds and cutoffs for. when a question is appropriate and how it gets embedded and which of the neighbors, like sometimes we may want to say, well, I will say this is a phthalate if the 100 nearest neighbors are also phthalates. That gives us like a boost of confidence to know this is. And so I probably didn't explain that super well. That's my rudimentary understanding. It's like that your
Mhm.
question gets embedded in the space, and then it's going to ask that large language model type question of the data that's in that space.
All right. Thank you so much. And thank you everyone for your excellent questions. AJ, as I mentioned, people are really excited about this tool. There's a few more questions in the chat, but I do want to turn it over now to Alicia McCarthy from Turi, who's going to be presenting on some of our work in this space. So Alicia, would you mind sharing? So Alicia McCarthy is Turi's senior safer chemical scientist. She works directly with companies to test safer cleaning and disinfection solutions. She's also an adjunct professor, preceptor for student capstones, and the manager of a steady stream of student projects, one of which she'll be presenting on today. All right. Thank you, AJ and Alicia. It's up for you.
Thank you, Agnes. Hi, everyone. So today we're going to be talking about and highlighting some of the work, particularly on one project that relates to this webinar topic that I had a student work on about evaluating effectiveness of AI tools. We're going to be talking about the large language models or LLMs in extracting regulatory relevant data, specifically around data sets that we actually already had that we had assessed on carbon nanotube studies. So to kind of give you a little bit of background, as Agnes mentioned, we have the opportunity because we're located at UMass Lowell to engage with various students of different majors and backgrounds. This was a project that was kind of poking in my head after having conversations with Gabriel and just in general about AI use, especially within this sector. And Arthur, who was a graduate master's of public health student that we got for 2 semesters focusing in epidemiology, really got excited about this topic and dived in and did an amazing job around it. And the purpose of this project was after having conversations with my colleagues that assist with gathering data on the Science Advisory Board or the SAB for the Toxic Use Reduction Act. I ended up learning that they tend to have to collect information after getting questions from the Science Advisory Board to follow up on. And I started to wonder, where could we leverage AI to be able to help kind of answer some of these questions or look for opportunities to gather more data that maybe the normal person can't see when they're assessing them. So I do want to highlight this has not been implemented into SAB. This is a theoretical thing that we looked at using data sets that were already answered, and I'll go into that. And I will be a little bit vague on the language models that we looked at and some of the data sets because we do plan on publishing this for more guidance. So I wanted to highlight that. So for those who aren't familiar with our Science Advisory Board, just to kind of let you know, they're an independent scientific body that was established under the Toxic Use Reduction Act. They provide technical and scientific recommendations for listing, delisting, categorization. And we actually have, I think, Karen Thomas that is on. So if you ever have any questions about SAB, she also is one of the people that collects data on that as well. And those that are on the SAB have various backgrounds, as you can kind of see on here. I listed a couple areas, and they are to serve as that independent role. So Turi will collect that data on the chemical of concern that we may want to list, delist for a categorization. They'll take a look at that and have those conversations. So as I mentioned, some of the challenges from talking to them that kind of popped into my brain was, they're going and diving into hundreds of journal articles and data sets. And these questions, they try and do a turnaround quickly because especially if the Science Advisory Board has questions, you want to give it in a timely manner so that way they don't forget, or maybe if they have a certain position, like we can really kind of give that information quickly while it's fresh in their mind to give it back to them to think about and keep the ball rolling. And that could be a lot of work, especially as a state organization. You're thinking bandwidth, how many people you have on hand, and how much information you're parsing through. So manual extraction can be time consuming, although important. But when you're dealing with, especially the SAB, from talking with my colleagues, you know, you get comments back also, especially for public comment from industry or lobbyists that have that bandwidth and stakeholders to really kind of dive in and become specialists in specific areas to answer and provide extensive comments or feedback, faster, especially during those meetings. So that's kind of where this kind of came from, of like, where can we use this as a tool, not as a standalone, but to be able to maybe streamline it or even the playing field potentially. So for this particular project, we decided to take the carbon nanotubes, both single wall and multi-wall studies that were already went through the SAB process. We had the questions that SAB had provided for TURI, staff responses and comments back. So we had answers already. And what we wanted to do was to assess 5 different large language models that were popularly used to see how do they handle reviewing this data set, especially journals, and how accurate or close to the answers that we would find for when we give it all those journal articles and data sets, could it be able to answer that? And before doing that too, I had Arthur go in because we wanted to review the journal licensing, AI use policies, because that's really huge. And what does that language actually mean, which I'll go into what we found. But I also had him go through, and there is online, you can look if you're interested. There are prompt engineering educations that are free and available for you to take that can help you if you're not familiar on how to make really impactful prompts. It can guide you through that process. So I had him take that so that way he could develop exact text prompts. So that way, when we were assessing each of these large language models, we could really compare side by side and looking at what those prompts actually provided for us. Out of 120 studies, we took 15 from single wall carbon nanotubes and 15 from the multi-wall carbon nanotubes, because this was just a pilot to look at it. And then we tried to process through. We did 8 prompts per study, 1 per variable that we were looking at. So you can kind of see here, I have a table 1 of the variables we were looking at, and that's from feedback from my colleagues as well, of like, what are the key areas that they find that they really, have to dig in, and a lot of the questions that were asked as well. And then what we tried to do was we compared the outputs and analyzed error patterns. So we wanted to see like how accurate it actually was when you ask those prompts. Did it miss data? Were there omissions specifically? And how correct was it? Did it hallucinate or have issues with being able to look at that data? And then we assess feasibility and just really understanding. And we got feedback from staff members of like how realistic this was to actual real world use and how they engage with SAB. So some of the key findings that I really wanted to highlight for this is that all of the LLMs, which are commonly ones that you are probably familiar with, showed generally reliable accuracy. The biggest issue we found was omissions. So that meant that it left out information. So if we queried it to look for that specific information that we were looking for, it was accurate, but it would leave out specific responses or answers. But for the most part, it does best for these different large language models with clear structured information. So when it is, data tables, specific areas of highlighting the like what the results were, it did a great job of pulling that out. Where it was challenging was when, especially with terminology, if there was variance in how people in those different journal articles use different terms, if they were exact, exposure details, and knowing how to find that was some of the challenging fields where we found that omission was largely an issue. these are really great tools, especially if you have a large literature set. And also if you have data sets that have repeated patterns. So if you want to look for pattern recognition that maybe we can't see from the human eye, but you have over 100 articles, it could look for patterns that maybe we don't even think about. So we found that this would be a really great tool to potentially use in the future. What we did find for journal licensing was that it does limit AI use. So you can upload PDFs depending on most of the journal articles that we had said you could use it for that. But as long as they could guarantee that it wouldn't retain that information and save it. So a lot of the paid versions, if you have them, so especially with enterprise subscription, if you're looking at like ChatGPT, those ones actually guarantee that. The other option that you have that you might need to have expertise in is you can actually make a local network offline LLM. So you could load all your data and do assessments, and it's not contributing to a larger language model. So that might be an option for you if you want to almost have like a query that you can review and use as a guide. Other things that we found were operational constraints. So file size limits, zip files were the best option, data handling policies, and just the suitability for regulatory and research context, like where do we use it? So when we talked with SAB and Arthur presented his findings, we had the best case scenario where we were given the answers and the questions to be able to check that. But we were told that usually when they have that question, they would have to go in and find those articles first and then do that. So we already had those articles ahead of time. So this wouldn't be great for if you don't have your data set or journal articles ahead of time. And that's why I kind of wanted to give like final takeaways is these are great for after literature when it's identified. And I actually listed a couple of really great literature mapping tools. And these are more non-generative AI machine learning map citation ones. Lit maps, I absolutely love. Connected papers and research rabbit. So that can also help with streamlining the process. And this doesn't take away from us actually being a part of it. It's really important to have that human aspect to verify things and check stuff. But
Alicia,
oh yeah,
this is all excellent insight, and I'm sorry that I'm going
no,
to
you're
transition
fine.
us to our last speaker.
Yep,
This slide is incredibly helpful, and I really encourage people to look. If you have any final words that you want to wrap up with, any like final takeaways that you really want to highlight,
yep,
but then I will ask if we can transition to Jakob. Thank you.
yep. So yeah, basically this hasn't been implemented, but I think it's worth exploring, especially to be able to help in these areas where we need bandwidth. So we're hoping to publish it. So please feel free to ask if you have any questions. Yep.
Yes, so Alicia will be available in the chat to answer questions. Sorry to have to cut you off.
No worries.
I was not the greatest at looking at time earlier. Yes, and please stay tuned for this work being published. Arthur and Alicia did a ton of work in this space, and we're really excited to be able to hopefully publish that soon. All right, Alicia, if you wouldn't mind stopping sharing. Jakob, I'm going to ask you to share. So Dr. Jakob Kostal is an associate professor of chemistry and director of the MS program in environmental chemistry and green chemistry at GW in DC. He also leads a research group developing computational methods for the design of safer and effective chemicals. Dr. Kostal is also the co-founder at ToxFix, which is a suite of predictive tools that's helped pharma and personal care industries reduce animal testing over the past decades. And he's going to speak on all of his work now. So thank you so much for joining us.
Well, thank you for the invite to you and Pam. So my talk today is largely focused on what we do on the academic side. So we're trying to bridge some of the recent advances in AI and what we know well, which is physics-led modeling. So using quantum mechanics and related approaches to help develop new protocols for designing overall safer and better chemicals. And as Agnes mentioned, outside of this academic design work, we're also heavily engaged on the commercial side, building predictive tools largely for pharma and personal care to mostly protect workers from exposures to occupational diseases like skin and respiratory sensitization, carcinogenicity, mutagenicity. Right. So talking about design, Let me see if I can. All right. So it's, when you look at our track record, I would say it's not difficult to see why we need to design new chemicals as opposed to just select from existing chemicals. I would say the first argument rests on sort of the documented flaw in our product development paradigm, right? Which tests for safety and environmental effects and fate in the downstream of the development, either when it's required by regulations, which is a relatively small percentage of the whole industry pie, or because of documented adverse effects after commercialization. So you have that public outcry, and that leads to some changes in the way the chemicals are used in particular products. Unfortunately, we then proceed typically to come up with substitutes that are often as bad as the compounds that they're replacing with. The substitutions of BPA with BPS or BPAF and other variants of bisphenol A are kind of the perfect case study for this. So in the end, it's sort of this self-inflicted game of whack-a-mole where the public and environment health bears the burden of these chemicals. Now, based on EPA TRI's data, if you go and ask the industry to replace chemicals of concern, by far the most common explanation for why this cannot be done is that they have no substitutes. So our pitch for the past 10 years or so has been we really need a multifaceted design approach to come up with new chemicals, and this needs to happen in the upstream before the chemicals are developed and commercialized. So how do we design? In our mind, there are these two sort of borderline approaches and then anything in between. I want to start with what we call the irrational one, because that's sort of the newer kid on the block and one that I would see has more promise. It's essentially a brute force assessment of all plausible chemical solutions, which can incorporate screening of existing chemical space, but also previously uncharted, sort of a new virtual chemical space. You can then parse this space by properties that underscore the design vectors that you're interested in. And I mentioned this is the more promising approach, and I would argue that that's largely because of the increase in available compute, which has largely followed Moore's law, so doubling every 2 years or so until about 2010, I would say, and then we see a very fast growth. So going doubling every 3 to 6 months. So bottom line, we have the models, we have the computing power now to see many more possibilities of what can be made and what can be made useful from some of these chemicals. Now, outside of this irrational, there's the rational strategy, which is sort of the more traditional approach where we consider existing chemicals, right? And then we sort of perturb their structures or modify their structures to improve their properties. And here again, we are thinking of the relevant design vectors that would drive your function, so your intended function or performance, would drive safety and would drive depletion, so the chemicals do not persist in the environment. And probably I should make it clear here that both are valid. So the rational and irrational can play together quite well. They are complementary, and you may want to pick one versus the other in different scenarios. Now, knowing the strategy, you can think about the methods to support it. So this is what we started thinking about some 15 years ago. I want to start with hazard as one of the design vectors. For us, the main source of inspiration was the pharma industry, mainly drug discovery. It's a field that's heavily regulated, so has adopted this multifaceted design early on. And while you can make an argument that the cost of developing a drug in the order of billions of dollars is prohibitive for other sectors, the computational component that happens in the upstream that every pharma company now uses, that can be easily translated at a relatively low cost to the commercial chemical sectors. Now, looking at the evolution of what that means, that computational bit. So if you follow the timeline in the 1960s, that was largely design informed by expert rules around molecular fingerprints, progressing into more robust mathematical models or QSARs based on structural indices and Fiskin properties. And over the past 25 years or so, adopting more complex, often physics-led simulations of large biochemical systems, and then incorporating machine learning and AI to capture these nonlinear and often very complicated relationships between the structural variables and the biological outcomes. Now, the key message, right? Very little of this has to do with the advances of the methods themselves, right? So the state-of-the-art QM really dates back to the 1960s, the density functional theory. And we have been tweaking that since, but that's been the last transformational change. AI goes back to the 1940s. Right? So most of this progress is not because of methodological advancements, it's because of increases in compute and availability of these resources. Now, if you compare this to the trajectory of predictive talks, I would argue the field has been largely stuck in where the pharma field was in the 1960s and 70s. So the paradigm of using QSARs and structural alerts. Now, we have been pushing for changes on this front, and it looks like we may be on a cusp of sort of regulatory advances for some classes where there is sort of willingness to embrace more advanced physics-led techniques, but the change has been slow, certainly much slower than what we have seen in the drug discovery. So the value proposition for us was, in safer chemical design, is take what pharma has built and repurpose it for green chemistry and predictive talks to design overall better commercial chemicals. Now, I can't deny my Eastern European nature. So let me start by telling you why this will not work, or this is why we have encountered roadblock after roadblock when trying to do this. So the first challenge is if you're designing something that's safe, you're trying to prove a negative, and that's very hard to do. In fact, you can't prove a negative. It's a probabilistic function, right? So you can only make something safer, but even that is challenging when you're dealing with this enormous complexity and uncertainty that's the biochemistry of toxicological pathways. So the most common scenario that we encounter, right, is you take a molecule like this diethyl maleate, which is a skin sensitizing plasticizer. You rationally redesign it by blocking the mode of action for skin sensitization, which has to do with 1,4 addition on that double bond. And you come up with a perfectly good substitute, which is an diethyl phthalate, which no longer sensitizes, but now is a very good endocrine disruptor. So you're back at this whole whack-a-mole kitty thing, right? So you have fixed one problem and you have introduced another problem. So what can we do? Well, we're taught to be sort of reductionist in the way we solve complex problems, which has become problematic for us when you're trying to reconcile all these interdependencies and limited knowledge. So our strategy has been, you can balance this high specificity of known modes of action, given the chemical class that you're dealing with more general reactivity and bioavailability behavior to then minimize those unintended consequences. Now, of course, this is very imperfect. The first trade-off that you deal with is you lose some resolution into what you can predict, or in terms of design, how refined versus granular your design space is. But on the upside, you have not lost robustness of your models. And in that regard, you can make an argument that this is a trade-off that's acceptable because the underlying in vivo data that we have to train these models has such poor reproducibility. It's not unusual to see somewhere between 50 to 70% for binary data. That what we are choosing to kind of gloss over in this generalization is not going to be the bottleneck in the overall workflow. Now, of course, that's not entirely true. There are consequences that we likely can't escape if we start to generalize how we describe most of these pathways sort of non-specifically in terms of reactivity and bioavailability. So what you may be inadvertently sort of impacting is your other design vectors, right? So we're talking about not just hazard, but we're talking about performance, which is the intended function of the chemical. You're talking about depletion, so various forms of degradation. Now, for us to see how much of a problem this is, we wanted to figure out a case study where we would sort of think in terms of multiple dimensions at the same time for these design vectors. So I want to walk you through this very quickly. It was a study on pesticide active ingredients, or AIs. We're trying to reconcile indirect photodegradation, where the pesticide degrades due to oxidation on contact with chromophoric organic matter, We looked at ecotoxicity, so safety toward aquatic species, and then the intended selective toxicity of the active ingredient. We started with photolysis. We built this tiered system using, there's very limited, like for most endpoints, there's very limited experimental data. So we expanded the training set using high-level quantum mechanics modeling, which essentially build out our training set for the more cost-effective QM approaches we then use for predicting new structures. We then took this sort of highly predictive QM model, which was based on very simple statistics. They were nonlinear models, but they were essentially 1 to 2 descriptor models. We integrated it with our previously designed guidelines for ecotoxicity, which are, again, somewhat simplistic. They're just based on bioavailability metric and a reactivity metric that's derived from frontier molecular orbital theory, so telling you how electrophilic, essentially, a compound is. And we assessed this over, I think it was over 16,000 pairwise combinations between existing pesticides from the EPA registry and known chromophoric organic matter molecules. We color-coded the results for both ecotox and degradation to support easy decision making, and we put it into a database, which, if you're interested, you can access from our group's website. Now, as for design, we developed these correlations between underlying substructural features and photodegradation metrics and overlaid it in all 3 vectors. So you have depletion function and ecotox in this very simple design space that's defined by reactivity and bioavailability. You can see in that sort of design space different parts being color-coded based on what would constitute an acceptable range of metrics for that target vector. So what makes an effective pesticide versus an insecticide or specific mode of action like ACH or acetylcholine esterase inhibition. Now, with this in place, we could then take existing pesticides and modify them to improve the properties. So, we could take this particular organophosphate here, and we could change the substituents on the ring, and we would know which way that's going to move us within this design space. Now, there's a clear deficiency to this approach, right? And that's the fact that you're operating all 3 design vectors in the same metric space, right? Which results in direct trade-offs. So it's better if you can orthogonalize, right? You can uncouple some of these, like you can uncouple selective and unintended toxicity. And the way we do this is by considering explicit target interactions for function. Here's a short demo. I think I have a video. Let's see if that plays, of how you can take, this is, I think, an organophosphate pesticide to understand the binding in acetylcholine esterase, and we can perturb the structures by changing the substituents and record the binding. So this is capturing very minute differences of the active site in, say, the target species that you want to kill with this pesticide versus a target species that you want to leave unharmed. And this method is taken directly from drug discovery, from lead optimization. So the way you modify your hits to get closer to the actual API, the active pharmaceutical ingredient. So now you have partly orthogonalized the different types of hazard. You may still want to orthogonalize or separate the photodegradation and the hazard. Here we found that because general ecotoxicity in our model is mostly driven by electrophilicity. In fact, most toxicants are either electrophiles or pro-electrophiles. So they are metabolically activated to become electrophiles. You can sort of capture that with your modeling. Photodeg, on the other hand, is driven by nucleophilicity because these substances get oxidized, so the electrons are pulled from a different orbital that would define electrophilicity. So you can separate the reactivity by considering these different molecular orbitals and energies that participate in the underlying reactions. So this helps, but there's another way that you can do this, and that's to open up the design space by adding another route of depletion that doesn't just rely on electronics and reactivity, and that's to, for example, consider biodegradation. I don't have a lot of time, I think, to go into detail here, but half of our efforts have been focused on developing a good model for biodegradation where we leverage pharmacophore matching approach from drug discovery, which is essentially comparing compounds for their shape and feature distribution to compounds known to degrade well, and paired this with quantum mechanics to quantify the electron density flux that happens in phase one metabolism. The computed metrics are then synthesized into a predictive model using decision trees, gradient boosting, or neural nets. Now, this is a collaborative project, I should mention. We work with Alexei Lapkin's group at Cambridge. We also work with the ACS-GCI Pharma Roundtable that's interested in next generation in silico tools for biodegradation. An important building block, right, of safer chemical design, especially when you want to orthogonalize that depletion route from the hazard route. Now, before going forward, I should, as just a side note, in the context of the previous talks, in most of our tools, we rely on physics and traditional statistics because the interpretability that Gabriel talked about really matters. Now, for most hazard endpoints, there just isn't enough quality data to train your AI models without overfitting. And so you encounter these unpredictable activity cliffs in external testing. Essentially, the way a neural net will try to mimic the complex relationships that exist between your inputs and outputs will simply not approach reality, what these real relationships are in a limited data set, right? And that's even more true for transformer models and LLMs. And from a practical sort of user perspective, most users will prefer to have a lower performing tool that's robust, one when you will know when the model's going to fail. That's more useful to them than having something that's internally high performing but has these unpredictable failings. Biodeg is sort of an exception for us because we have almost 10,000 reasonably reliable data points in a binary yes or no kind of a partition. So we can examine the use of AI here. But for a lot of the other hazard endpoints that we deal with, it's largely traditional statistics and QM modeling. Now, it's fair to ask you, what if you still fail, right? So all this orthogonalization in your multidimensional design space, that can still all lead to failing. So if none of this, right, so the question is, can this lead you to an acceptable set of trade-offs for a given chemical or class? And if it doesn't, right, at that point, you really have to go beyond what's known in the chemical space. So to put this in numbers, in terms of how big of an sort of unexplored opportunity we're talking about for pesticides, the EPA registry has on the order of about 10 to the 3 active ingredients. The zinc database, which is commonly invoked in drug design, has about 10 to the 8. The entire space for innovation that's available is about 10 to the 60, right? So this is really the proverbial, single grain in a whole beach of sand. Like we have so much more to explore. So from a perspective of where you should be focusing, if we are just focusing within what we know, we're really, tying hands behind our back, right? So we need to, that again, going back to the initial irrational versus rational partition of how we design, I would say the brute force approach to trying to scope and understand this vast virtual space of potential new chemicals is the way to go. We have been working on this for 2-3 years now, largely using transformer-based architecture to design new virtual chemicals. We are focusing on bio-based feedstock. So we build compounds that are easier to degrade. Now, because bio-based feedstock is a priori lower in toxicity and higher in a potential for degradation, the added bonus of this is a dimensional reduction, right? Where we are essentially avoiding that complexity or the necessity of proving a negative in safety and are going back to what historically we know how to do pretty well, and that's to prove a positive, to prove a function for a chemical. So think of this as sort of tackling the same problem from the opposite end, not starting from a functional chemical, but from a large repository of bio-based solution that can be parsed to find a function. for us, the process starts with AI to generate a large repository, as I mentioned, of what can sort of be made from these platform chemicals. And then we invoke a paradigm that's very common in drug discovery, and that's to parse this or screen this space down to look for analogs of existing functional products. So going back to pesticides, this means finding, say, inhibitors of targets that are relevant to selective toxicity of of the pesticide class that we are interested in. Now, the premise was we can find bio-based analogs that are similar in the ways that matter to the function, but not in a way that drives hazard. Once we identify these analogs, we can then modify them, and if groups that might impact degradation or toxicity are introduced into those scaffolds, then we can rescreen them with the approaches that I mentioned previously. Now, to be clear, in real world applications, right, you're not completely getting rid of that multidimensionality problem, right, and the proving of the negative quote unquote problem. You're just minimizing the needed impact of these models on the solution. You're introducing them later to a controlled extent that you need them for that function to be there. We're still building out this database. We're currently close to 1 million structures from just the bio-based feedstock. But there are already some promising candidates that emerge that seem to outperform, or at least compete well with existing pesticides while minimizing the unintended toxicity. I don't want to go too much into detail because this is still very much ongoing and we haven't finished that entire space scoping yet. But what's become apparent is that one strategy is to do this mimicry where you look for compounds that in the ways that matter to your function look like the compounds you're trying to replace, but lack those inherent toxicophores and are inherently more biodegradable or generally degradable than the current pesticides. But there's another approach, and that's the one where you go beyond just simple mimicry and you look at the biological requirements that these compounds have to have in order to be functional. So you don't have to make your replacements to look anything like the current pesticides, right? You can start looking into much larger molecules, right, that may have more favorable electrostatic binding across the board, taking advantage of other parts of the binding site in the target of interest than the existing pesticide. And this is useful. This is useful because you lose something in those toxicophores you're trying to get rid of. Often you lose this sort of irreversible inhibition for some of these MOAs, which comes from covalent binding. So to account or to compensate for this, you can build up a larger system which has weaker electrostatic interactions, but has many more of those. And as a total system can compete in terms of potency. Now, before taking questions, I got to credit the students. I showed you the pictures of all the students that have been over the years contributing to all this work. Again, on the academic side, the professor takes all the credit and the students do all the work. So that's a very unfair division of labor. So here are all of them listed. I should also mention our support and a shameless plug-in for a master's program in environmental green chemistry, where we are trying to do or teach students what I just mentioned in our research, sort of bridge this green chemistry world with predictive toxicology, computational modeling, and data science. Thank you all.
Wow, thank you so much. Lots of food for thought. Do we have any questions? We have about a minute. We have in the chat Jill Verns appreciating your acknowledgement of the student contributions. Yes, I agree with that. Thank you for having them up there. All right. So we have a question from Ivan, which is when looking at interactions between a proposed chemical and an active site, was QM/MM or tools like Autodoct used? And also in terms of resources, I would think that predicting binding is computationally expensive. Is this the case, or is AI more computationally expensive? So if you could speak to either or both of those questions.
Yeah, so that's a great question. For the target binding, you kind of try to make it into a funnel. So at a stage where you're screening a lot of chemicals, you have to use cruder approaches because of those time constraints. So you would start with some sort of ligand screening where you look at similarities to a known chemical space of inhibitors. That is probably less expensive than structure-based design, where you're actually considering the target, whether it's using Autodock or other docking software. We, in our initial sort of screen, rely on our own in-house modified version of Vina, it's an Autodock Vina. It's a version of the same program. Very crude force field, so there are a lot of approximations made there. But when we get to the final refinements, especially when it comes to the modification of any potential promising hits to become sort of leads for substitution, we use a more rigorous free energy perturbation approach, where you have a full force field, you have a solvation of these active sites, and you're actually computing a relative free energy of binding. So the complexity and expense increases as you manage to reduce down the chemical space. On the AI side, so we are mostly users. I'd like to think we are enlightened users, no, but we are not developers or experts. A lot, for the things where we need more insightful contribution, we collaborate. For the virtual synthesis, we use IBM Reaction, which comes out of molecular transformer program. The expense of that is, again, per transformation. So say pairwise examination of a potential reaction. It's not very expensive, but we're dealing with the sheer number of potential combinations that kind of arise exponentially as you start expanding your design space, and you're using the virtual products that you have built to kind of scope out new reactions, and you build these generations of products, right, layered on top. So you have sort of second and third and fourth generation that's created out of your initial virtual product. So of course, at that point, the overall cost goes up exponentially as well. But it's a different type of cost. One comes out of just the sheer number of possibilities, and the other one comes out of how well or how realistic you are in the representation of the system of interest.
Thank you. That was a very helpful and thoughtful answer. Well, we're a couple minutes over time. So I just want to say I'm echoing what Bill Judd said in the chat. Just an immense thank you to all of our presenters today. I feel like I learned so much, and I can't imagine how much more we could learn on this subject. Thank you for joining us for this 90 minutes. I really appreciate it. Yeah, if we could just get one more like virtual round of applause for our presenters. As Pam said, we'll be sending out a survey and posting the slides and recording on our website. If you're a planner who needs credits, please fill out that survey so we can get you that certificate. All right. I guess I will say happy holidays to everyone. Thank you so much for joining us at this webinar and throughout the course of the year. And yeah, have a great Tuesday, everyone. Thank you so much.
Thank you, everybody.